And what you want to do then in yours, and it's all on that handout, and everything is okay except for the LF over D part. What you want to do is do this. Given we want to take a force, don't hurt yourself with that. Another kind of spring we have is called a torsional spring, which is like a mousetrap, rat trap. And I sometimes pass that around to my class, but I'm always worried they're going to hurt themselves on a mousetrap. And they don't usually, but I have to warn them here as well. Be careful. Anyway, force is 500 newtons. All SI here. At deflection is going to be 50 millimeters. And music wire is the name of this material. This one over here is music wire. The strength equations vary with the different kind of wires. They're different kind of wires. Music wire is a wire they use on kind of the smaller springs, up to about 5-6 millimeters. Now, that big spring looks big, but its diameter is only about 6 millimeters. So if you'd have a spring with 10 millimeter wire, it's a huge spring. Something you might have in a truck or something. Anyway, back to this. Plain ground. Plain ground ends gives you this. Plain ground, that equation. And the other thing is avoid buckling. And now here's what you have to do. What do you call optimal? Optimal? For optimal, the wire diameter D, coil diameter big D, and free length. LF. Those are the three things, only three things. But reviewing this again, they are interchanged a little bit. Okay, the wire diameter, little d, going to set the strength. So if the thing isn't strong enough, you got to make it bigger, little d. If you make a bigger little d, you lower the strength. So on one side it helps, and the other side it hurts. So that's a problem for optimization. So the little d tells you how much load you can bear. Obviously 500 newtons, you can't have something as big as a hair, like 0.5 millimeter or something isn't going to do it, nor are you going to need something huge, a big truck thing. 500 newtons, by the way, is a little more than 100 pounds if you are not familiar with SI. It's a little bit more than 100 pounds. So it has to be somewhere in the middle there. So you have to design that wire that fits all these strengths. And then the coil diameter impacts both the stress and the deflection. And you have to make the deflection come out to about 50. If in your optimization you're off a couple percent one way or the other way on one of these, it's okay. But you have to do that optimization and to get the right deflection. So it depends on that. The big D to little d ratio is constrained within that bracket. And let's see what else. Then you want to design a free length. So the bigger you make the free length, the more deflection you get, the more likely it is to buckle. So it's a problem. It's going to buckle if you make it too big. I can show you when I get those back what I mean by buckling. So you don't want to make it too big or it buckles. Here's a spring that I'm going to try to depress in compression. If I'm not careful buckling, it comes out like that. It just bends over. That's classical mechanics failure mechanism, buckling. And anything in compression can do that. And once it buckles, it loses its strength. What you want it to do is stay straight. Now, you can hold it with your hand, but you're not going to be there to hold springs for the rest of your life. So you want to design it so it doesn't buckle. These little jobs, that buckles pretty easily. So that's the last criterion, that you want to design against buckling.